So I am going to leave the slides locally in case anybody wants to follow up in more detail. And most of what I'm talking about has been published. Right at the end of the talk, I'll get on to some new work. But because I wanted to make this very much an expository lecture, I'm also going to indulge myself initially with a few general comments on how I work as a statistician and the kind of view of the subject that I've evolved over a career, which has taken me generally from starting off as a very theoretical research student in stochastic processes through to a very applied person working at the interface of statistics, public health, and a little bit of health informatics. So for me, it's been a long journey leading me eventually to spending a non-trivial proportion of my efforts working in Africa, which is what I'm going to be talking about today. Okay, the other thing is, in case I forget to say it later, nothing that I do in this area of any value is done alone, and these are just some of the people who've helped me. In Lancaster, in Africa, APOC, you'll hear more about later, and particularly in the US, my association with Columbia is through meeting and being inspired by a tropical disease entomologist called Dr. Madeline Thompson, who works at Columbia. So the indulgent bit, I just want to sort of say one or two things, and I apologize to the wise heads who may either think this is stating the obvious or actually think it's nonsense, but this is my view of what statistical modeling is all about, which is that models are actually devices. They're devices that are there first and foremost to answer somebody else's question. And the requirements of a good statistical model, the first one is expressed in a characteristically indirect, cautious statistical way, which is, whoopsie daisy, that a model should not be demonstrably inconsistent with the data. Okay? In other words, getting a beautiful fit is fine, but it doesn't happen very often. But you shouldn't have a demonstrable inconsistency with the data. If the underlying science is well understood, your model should respect it. In many of the problems I work on, and in particular in most of today's talk, I'm building what I call empirical models, where the scientific knowledge is really extremely limited. And so you do have to fall back on models which really are very statistical in nature. But if there is any scientific mechanism underlying your data that people know about, I do think it's very desirable that that is incorporated. Now, the great thing that I think statisticians have over mathematicians when they talk about models is that statisticians have an explicit paradigm for penalizing complexity. Okay, when we add parameters to our models, we don't just want a better likelihood because we'll get that automatically. We want a materially better likelihood, and so we make extra complexity earn its keep. And I think that's very important, and corollary immediately to that is that I think you need a very good reason not to use likelihood-based methods of inference. And whilst I never met David Sprott, I think that's probably a sentiment he might echo, although I've noticed that in a book kindly shown to me by Stefan about an hour ago, in the southwest corner of the USA, there are clearly people challenging that paradigm and advancing the cause of non-likelihood-based methods of inference, and they may have a point, time will tell. Okay, so I want to just divert to a couple of animations to illustrate two things. Firstly, the difference between what I call empirical models and mechanistic models, and secondly, to emphasize that the way I approach modeling a set of data is not determined by the format of those data, but it's determined by the question that the scientist who collected those data wanted to answer. So both the data sets I'm going to show you in these animations consist of points which exist in a geographical continuum, and they also come time-stamped. In this case, 5 successive days, locations of cases to the NHS, the National Health Service in the county of Hampshire in southern England, complaining of gastrointestinal symptoms. These are data made possible through the launch in about 2000 of a 24/7 phone-in triage service within the NHS called NHS Direct, which sadly was a casualty of the Tory government's austerity policies a few years ago. But until a few years ago, we had a nationwide, consistent 24/7 triage service which collected where and when people were phoning in, asking for help with specific symptomatic problems. And this is what I call an empirical problem, because the question that we were trying to answer was, is there anything unusual about that pattern of incidence, or is it just what we'd expect? Because if something unusual is happening, the earlier you can detect that and intervene and do something about it, the more you can control something that might be a potential public health problem. So there's nothing biomedical about that. And in fact, these cases are not confirmed diagnoses of anything. They're simply people phoning in saying, I don't feel well and I've been sick and da-da-da-da. Okay, so you can't really expect to build a model that has any biology or medicine or biochemistry in it. You just need to understand the patterns and in particular have a mechanism for, sorry, a statistical method for deciding whether those patterns are unusual in any way. And I'm going to contrast that with a devastating occurrence in 2001 in the UK farming industry, which was a very widespread epidemic of foot and mouth disease, which particularly and most severely affected the county, essentially where I live. Technically, I'm not in that county, I'm in the adjacent county, but I live about here, and you'll see in the animation that this was a pretty devastating event for the rural industries in northwest England. Now, if I can reveal my incompetence, or miraculously my relative lack of incompetence, I want to show you two videos and contrast their appearance. So in fact, I want to show you the other one first. So this will remind you of the slide I showed you, which is the county of Hampshire with 5 days data shown, and there's a little box there which basically says that there is statistical evidence that the incidence here is unusually high. Whether that's of any public health significance, I would not presume to judge, but statistically you could call it an anomaly. Now if you run that animation, then this does not look very exciting, okay? It looks very much as though things are just popping in and out at random. And to a first approximation they are. But if you just subject these data to essentially standard non-parametric methods of estimating the moment properties of the underlying point process, the point process analogues of mean, variance, covariance, there are indeed occasionally these localized, we call them anomalies, in which you get evidence that there's an underlying risk function that is actually becoming materially bigger than 1, if you think of 1 as what you expect. And the height of our ambition is to be able to detect those with some reliability. Okay? Now, if I contrast that with the foot and mouth epidemic, and let's just go back to the beginning, and you can see that Cumbria, what you've got there is all the farms that were holding sheep and cattle at the beginning of the epidemic. And you can see that the epidemic started in the north and spread rather disastrously through, but you can also see that occasionally it did something which is biologically somewhat implausible. It seems to jump a long distance. That's almost certainly indirect transmission of infective material by people moving around the county. But you can see that there's a lot of structure to that animation that was not present in the first problem. And if you say, well, why might we want to fit a spatio-temporal point process model to these data? One of a number of possible answers is that the government didn't just sit and watch that happen. It had a policy of preemptive slaughter, okay, that if a farm was recorded as having foot and mouth, farms in the immediate vicinity had all their stock slaughtered. And they had to decide what the radius of that circle was. And I didn't do the original modelling. It was a group headed by Professor Matt Keeling in Cambridge University. They actually built a spatio-temporal model of spread within which they had to estimate a parameter which essentially was basically how far would an infection spread directly from one time to another. And that determined the policy. And my contribution was actually after the event, sadly, which was to say, well, I'm sure you've got the answer about right, but you've just given a point estimate, and I wonder if you could actually do some proper inference. And it turns out you can. But the point about that is that they're both just points in space-time, but estimating means, variances, and covariances for these data would tell you nothing interesting, whereas estimating means, variances, and covariances for the first data set actually gives you enough information to solve the problem. So in other words, methods need to be linked to problems, not simply reacting to a data set, right? So data needs a context and a question before you know how to analyze it correctly. Okay, so now we can move on to my one-slide summary of statistics, which is that we're trying to understand how nature works. And so we can conceptualize that the state of nature is some kind of stochastic process operating. And we collect data to try to get a bit of an insight into what that stochastic process is doing. And we have a reason for doing so, which is that there's some property of the state of nature that we care about. and we'll call that our target for prediction. So we can build models. Now I'm ignoring the at least as important and arguably much more important questions of what you do before you build the model, notably design a study. But once you're actually onto the modeling, which is what I'm talking about in this talk, you can think that the joint state of nature and data has to be that the true state of nature takes precedence, and so that should be modeled unconditionally. And the data only exist by virtue of the state of nature, so they should be modeled conditionally. And when we do prediction, we're simply applying Bayes' theorem, and we're getting a distribution which obeys Peter McCulloch's rule that the answer to a prediction problem is a probabilistic distribution. So we're using Bayes' theorem, which I'll be doing throughout this talk, but I want to emphasize, particularly in these hallowed walls, that we're not being Bayesian. That's an entirely different matter. Somebody who believes Bayes' theorem is true is not a Bayesian, they're just sensible, because it is true. Okay, so that's enough of the generalities, and I've managed to lose my pointer, and I've managed to find it again. So at long last, we get to Africa. Onchocerciasis, commonly known as river blindness, is spread by a biting fly, and the first European to describe what it's like to live in areas where that fly is existing in large numbers was John Hanning Speke, and it's clearly not nice being bitten by one of these flies. But it's worse than not nice, because if you are bitten by one of these flies, and that fly is infected with the parasites that cause onchocerciasis, and you don't get treated, then eventually you're at risk of going blind. And this statue, which stands outside the WHO headquarters in Geneva, is a kind of rather moving sort of metaphor, if you like, for the fact that one of the major public health problems in large parts of rural tropical Africa is that people go blind in early middle age owing to the effects of untreated, often undiagnosed in the critical moment, river blindness. Now this is much less of a problem than it was, but it's still a pretty major problem, and one of the reasons it's not as bad as it was is because of the WHO's actions against it. To see the extent of the problem, that's a map, a prevalence map of river blindness throughout Africa. Although it was only published in 2014, it refers to prevalence data that showed what the state of the disease was continent-wide before the WHO initiated a multinational control program that covered essentially all of the countries that you see coloured in that map. And that program was called the African Programme for Onchocerciasis Control. And it does what it says on the box. Its aim is to control onchocerciasis. And it initially tried to do that by attacking the fly's breeding sites with sprays, insecticides, and so on and so on. Didn't work. And so they then fell back on a really blunt, but it turned out to be quite effective instrument, namely, in communities where the disease is known to be prevalent, mass treat people with prophylactic filaricide. In other words, give them a pill which will kill the young parasites in their bloodstream before they can do any damage. If you don't have parasites in your bloodstream, well, take the pills anyway. And that worked pretty well because it was not a novel drug. It was a drug that had been in use for many years, was generally considered safe with no serious side effects, and critically was donated free by Merck, who built a factory which produced and continues to produce this drug, and it gets shipped to the docks in West Africa for free, and then it's the job of the in-country agencies, health ministries and their sort of spin-offs, to distribute that to the at-risk population. And just remind yourselves, that's a pretty big population over a pretty big area, and we're talking about the rural population. It's not a problem in the cities. I've drawn the map as if the whole of Africa was rural, but that's because most of it is. But this is a problem of rural communities. Okay, and in fact, this program with that acronym is no more. It's been replaced by an ambition to eliminate rather than control the disease, but it's early days to know whether that's feasible. But what happened some time ago was that it was noticed that although this drug was considered to be very safe, some people who were heavily co-infected with a second parasite called lower could experience a serious and occasionally fatal reaction to the drug. To give you a sense of the scale of that problem, there have been several hundred deaths due to the drug, but out of more than 50 million treatments, in absolute terms that risk is minuscule. But whatever number it is, you'd like it to be smaller, and it did cause an interruption to the program. Okay, thanks. An operational introduction, which was basically that, remembering we're dealing with a condition of remote rural communities, if, when you administer this drug, you have paramedics on hand to treat people who show the first signs of that bad reaction, you can probably save their lives. But you can't afford to do that routinely. So what you wanted to do was to say, where are the areas that are at high risk of people experiencing these adverse reactions so that we can do something about it. We can put in protective measures so that for the unfortunate people who do suffer the reaction, we can intervene and, with reasonable luck, save their lives. So that's why we get to the second parasite of the title, which is that lower lower in itself is unpleasant, as you'll see in a couple of minutes, but it's not life-threatening, and it has no permanent sequelae, but it became important because it was an impediment to the successful operation of the program for onchocerciasis control. So the remainder of this talk is an ongoing story of how I got involved in this maybe 10 years ago now, and I thought I'd finished with it shortly after when we published our paper with maps of the lower lower prevalence across Africa, and it kept coming back to haunt me in a good way, and it's still haunting me in a good way, and I think it's a mildly interesting story because at each step along the way there's been an interplay between field epidemiology, statistical methods, and most recently new technology, which is trying to get a better and better solution to this problem, which is basically how can we control the life-threatening diseases without putting people at risk by virtue of the thing we're using to try to treat them. That's what lower lower looks like when the fly first bites you, and that's what it looks like if nobody does a thing about it. And that program is not just meant to put you off the reception, it's actually because this turns out to be a rather key picture in terms of being able to operate on the kind of vast geographical scale that's necessary if you want to really achieve success in this program. So we will hear more about that photograph later. So now a very brief diversion into statistical methodology. The methodology that I'm going to use through most of this talk, most of the remainder of this talk, is called Geo Statistics, and that has its origins in a slightly surprising place, which is the mining industry in South Africa. And it was subsequently taken up by a young Georges Matterand, who, on national service with the French Foreign Legion, came across this work in the mining engineering literature, took it back with him to France, and as he rose from a young, promising scientist to be the head of the National School of Mines, he developed a self-contained methodology, la Geo Statistics, which was designed to solve problems of the following kind: spatially continuous process sampled at a set of spatially discrete locations. What can you say about the complete realization of the underlying spatial process? In the original context, you can think of that underlying continuous process as the ore that you're going to get out of the ground if you mine a whole area, and the data are the data that you get from exploratory digs, assay what you find and say, is it worth exploiting the whole mine or not? So that's a kind of very tangible problem. But the analogous problem is the one we're facing, because the first foray I had into this problem was when I was given these data, which are empirical prevalences of lower lower collected opportunistically by field epidemiologists going about their business for various reasons in Cameroon and drifting off into southeast Nigeria. And those, there's some redundancy in that picture. The circles are coded both by size and color in quintiles of empirical prevalence. And you can see in that picture immediately that there's a lot of geographical structure in the prevalence, and if you had to guess what the prevalence was at an unsampled location, there are substantial parts of Cameroon in which you'd be pretty confident that it'll be red or orange. And there are other parts, particularly over in Nigeria there, where you might hazard a confident guess that it's probably pretty small prevalence, but what do you do about all the missing areas? And that's the basic geostatistical problem. Okay, well, we'll get an answer which some of you will already have guessed in a few slides' time. Now, a few years before I got involved in this area, myself with two Lancaster colleagues, Rana Moeed and Jonathan Thorne, published a paper with the rather bold title of ModelBased Geostatistics in the Journal of the Royal Statistical Society, which we simply meant to mean the following. Geostatistics, when I was a young researcher, was developed entirely outside the statistical mainstream. It had its own terminology, its own methodology, there was very little cross-referencing between the geostatistical community based on Fontainebleau and their acolytes and the mainstream emerging spatial statistics community in Britain and the UK, who were basically building methods based on stochastic models for spatially correlated data. And all that Rana, John and I were trying to do in this paper was say, you know, geostatistics is just statistics. And therefore, you can apply general principles of statistical modeling and inference to it. In other words, you start by saying, what question am I trying to answer? You then design the study, and of course, sometimes you don't have the luxury of designing it, but even then, you can often selectively say, what data sets should we collate together to address that question? So in a sense, you're designing your collation of data where it already pre-exists for other purposes. In a happier world, you would always be involved in the design stage ab initio, but we all know that doesn't always happen. You formulate a model, you fit it using likelihood-based methods, and you answer the question. And that seemed uncontroversial to us, and so we started doing it. And one of the applications I subsequently applied these methods to was the lower-lower problem. So, to remind you, people heavily co-infected with lower-lower parasites are at risk of serious adverse reactions to the drug that's there supposedly to protect them from river blindness. And the current strategy, and current is pushing it a little bit now, but I think it probably is still just about current, is a very sensible qualitative argument, very old argument, that heavily infected people are more likely to be found in areas of high prevalence. Seems sensible. Therefore, as a proxy for actually finding people who are heavily co-infected, we will actually find areas with high prevalence. Because it's much easier, cheaper and safer to measure prevalence in the field than it is to actually do blood assays to find out the exact concentration of the parasites in the blood. And so we're going to map lower prevalence using model-based geostatistics. And the specific question that the WHO set as a policy directive was that they wanted to know where the prevalence was at least 20%. I didn't determine the figure 20%, no statistician did. It was the result of a complex and not entirely transparent series of discussions and debates by subject matter experts, health policy experts, health economists, and they decided that 20% was where they would say, that's a high-risk area, we want to be careful. So, what data do we have to inform this question? Well, we have the data I showed you on the first slide, not the first slide, on the slide with the coloured circles, and that's where we've basically done a rapid positive-negative blood test for lower. But we also know that these flies like breeding where it's hot and wet. And in tropical Africa, hot means low elevation, because it's nighttime temperature, minimum nighttime temperature in particular, that determines the viability of this insect for breeding. And we know it likes wet, humid conditions, so we use satellites to give us a digital map of elevation and a digital map of greenness of vegetation. This is an endemic condition, so we're not talking about what's happening here and now, we're talking about long-term prevalence. So we take satellite images, in the case of vegetation, averaged over an appropriate time period. And all that was done before I got involved at all. And the first thing we think of is a logistic regression model. So if you look at the empirical logit of prevalence and plot it against elevation, you get this picture here, and the line there I did draw, but I drew it after my entomologist friend, who I mentioned earlier, Dr. Thompson, said, the generally accepted wisdom is that these things can't breed over 1,000 meters in equatorial Africa. So you put a knot in your regression line there, and indeed you can see that there is this disastrous, for the flies, plummeting of prevalence, good for the people. It's leakage because, of course, the fact that people live at low prevalences doesn't mean that they spend their whole life, low elevations, doesn't mean they spend their whole life there. And so, somewhat pragmatically, I fitted this split line as the preliminary regression for prevalence and elevation. If you look at the relation with greenness, it's much simpler. And in fact, it's simpler still when, again, the people who know about satellite imagery tell you that as a proxy for greenness of vegetation, this particular satellite index is considered to be saturated at 0.8. And so in effect, anything above 0.8 is folded back to 0.8, and you get a very loose linear relationship. Okay, now you go a bit beyond that, because you don't need a statistical expert these days to fit logistic regressions with only 2 covariates. And you introduce the idea that there's some geographical variation that you cannot explain by the covariates, and that's where a stochastic process gets involved. And this is where a stationary Gaussian process makes its first appearance. And we model this with a very, very simple parametric model in which we have one parameter that says what the average of that stochastic process is. And basically, that's effectively going to be 0, because if it wasn't 0, we'd put it in the regression function. The variance sigma squared tells you how variable that unexplained variation is. And there are two parameters in the correlation function that tell you on what spatial scale does spatial correlation decay to 0, and roughly what's the shape of that decay. And you fit the resulting model adding on the natural sampling distribution of binomial by maximum likelihood. If you just fit the logistic regression model, you end up with this picture on the left-hand side showing you predicted versus observed prevalence. Okay? Not bad. And indeed, that relationship was published, and a map was published accompanying it, which showed the best predictions available from a logistic regression model. If you then add the Gaussian process, which is acknowledging that there's geographical variation that's not captured by those covariates, you get the scatter plot on the right, and you can see the extent to which that Gaussian process term has tightened in the relationship, and it looks not bad. If you then translate that to what the policymakers want, you get this map. And the hardest job I had in getting people to accept the use of these Gaussian process models rather than simple logistic regressions, which they understood. That's not meant to sound patronizing. I certainly don't understand the biology. It took me a while to sort of get across the idea that really the key question here is not, can you estimate prevalence? The key question is it likely that prevalence is high enough to be worrisome? And so in this map, you have got the raw data expressed as empirical prevalences. So blue dots are less than 20%, and they're size coded. Black dots are more than 20%. They're all the same size. But you've also got covariate adjustments, and then you translate the output of the model, remembering what McCulloch said, to a predictive distribution of prevalence at each location on the map. And it turns out that the regression terms are very effective at eliminating, putting to nearly 0 the probability that prevalence could be bigger than 20%. So all that stuff to the north, that's entirely driven by high elevation, dry ground, where the model is very confident that it doesn't know what prevalence is, but it's pretty confident it's less than 20%. The model is less confident at the other end. In order to have a probability near 1, which is dark red, that prevalence exceeds 20%, you really need some ground truth data adding to the covariates. And so you do see these dark reds predominantly, but not exclusively, where the black dots are. And in the intermediate hinterland, you can see pink, which is the 50-50 call. And it's rather unfortunate that the colloquial name for this map is the pink map, because pink means you don't know what's going on, right? But you say, clearly, we need more data. And this is where, sitting in your comfortable office in Lancaster, north of England, you have to be rather humble. Because the chappie on the motorbike here is an epidemiologist. And he's on a 28-day tour from Ouagadougou, the capital of Burkina Faso. And he's got instructions to find a certain number of villages in some broad area. And whenever he finds one, he has to negotiate with the village elder, explain why he's there. He has to get the villagers to agree to have their fingers pricked and blood taken. It's not very pleasant. 28 days later, he gets home. And the reason he's on a motorbike is because when he left Ouagadougou, that motorbike was on the back of a Land Rover. But at some point, the roads gave out, and he unhitched the bike and carried on. So what you don't say to somebody like that is, have you thought of putting your data on a regular lattice? Or something like that. You know, you have to think a bit operational researchy rather than high principled statistically. Now the other thing, and I think I'm there now, yes I am, the other thing is that even accepting all, you know, that you're going to get data that's spatially very inhomogeneously spread and you're going to have to do the best you can, on the kind of scale you need to make that pink map more precise, it is neither affordable nor arguably safe to keep on taking blood samples. And some of the workers in the program based in Geneva in Switzerland, but working, collaborating with people like the chappie on the bike, actually devised a very simple test. And this is the photograph I showed you earlier, And what Chappie on motorbike now does when he gets to the village is for each person who presents themselves, he says, have you ever suffered from eyeworm? No? Thank you very much. If yes, did it look like this photograph? If no, thank you very much. If yes, did it go away within a week? Remember I told you it's unpleasant but didn't have permanent sequelae. 3 yeses is a plus, everything else is a minus. And for the research phase of this exercise, of course, they then had to take blood to sort of check if there was any validity to this extraordinarily simple questionnaire instrument. And so here's the calibration data, which is color-coded according to where the study was done, and it spans from the east of the Democratic Republic of Congo through to western Cameroon. So it's geographically very dispersed. And the picture on the left is the one that I was shown when I first got involved in this phase of the project. And the people who were analysing those data fitted a quadratic to prevalence. And so, of course, I took a sharp intake of breath, because if you're teaching a course in generalised linear models and somebody fits a quadratic to prevalence, you probably wrap them mildly on the knuckles. But if you translate to empirical logits, then although there's, it's far from perfect, I was pleasantly surprised, indeed, there was just a hint of smugness, I confess, to see that it looked roughly linear on an empirical logit scale. And so that's what we did. We fitted a linear functional relationship on the empirical logit scale, and we back transformed, and we got these calibration curves from each of the 4 countries where we had data. And remembering that the operational decision is around 20% prevalence, we were very pleased that all these curves look pretty much the same. Now they go all over the place at high prevalences because we've not got much data there and because the model's not a perfect fit. But basically that reassured us that you could use, with an appropriate calibration, because it's not 2020, right? That you could use RAP-LOWER, as it's called, Rapid Assessment of Lower-Lower, as a proxy for parasitology-based data. And that is where the map of prevalence came from, right? Because you could scale up then, and we ended up with about 3,000, 4,000, 5,000 villages surveyed, and we were able to map the distribution. So that was a step forward. Those are where we had survey locations, and that's our new updated version of the pink map. It's not quite as good as it looks, because of course I've now looking at the whole of Africa, and if you hone in on Cameroon, where I was a few days earlier, those cream bands of uncertainty are not trivial. There's a lot of people live in those bands, but it's much better than it was, because instead of just having a couple of 100 points in Cameroon, we've now got, I think, nearly 1,000 in Cameroon and many thousands Africa-wide. And so what we've done there is actually say these are the areas that you need to be concerned about. And in the meantime, while you're wondering what to do about that, you can, with impunity, treat in the blue areas. Okay, now, this is the recent work. I thought we were done at that point, but then we come back with the question, couldn't we do better? And remembering that the biological hypothesis, and it's, I think, well established, that the individuals who are at high risk are those who are highly infected with lower parasites. Can we actually use the data on prevalence to predict how many people are highly infected? Because we start with this working hypothesis that high prevalence areas are likely to contain people with high levels of infection, ergo there's some correlation. And if that correlation at community level persists at individual level, which is not a given, as all of you will know, have heard of the phrase ecological bias, but if that relationship persists at individual level, we could actually use prevalence data to predict the number of highly infected people within a community. And that would then mean we could really decide whether we're talking about at most one and probably no individuals at risk, or several, in which case we've got to be very careful. So now we have to reformulate our question, because instead of just saying, can you identify or can you answer the question, does this community have a prevalence greater than 20%? We're now asking a more refined question, which is, in this community, how many people do you think have a level of infection greater than a value that experts in the biology of the disease, I guess, think is a risk to that individual? And for illustration here, I'm using 8,000 parasites per milliliter of blood. In fact, the currently accepted threshold is higher than that. It's 20,000 parasites per milliliter of blood, which gives you some food for thought if you think about it. But anyway, can we do it? And so the idea initially, because this is what we were told, is that we've got research data on individual levels of infection, but we can't routinely, for reasons I mentioned earlier, go accurately counting levels of infection in individuals. But we do now have this quick way of estimating prevalence. So if I simply give you data in each community on the number of individuals tested, the number testing positive, and any covariates you think might be useful, can you actually compute a predictive probability that an individual sampled at random from that population will have an infection level greater than 8,000? Okay, so back to research data, which is again geographically much more restricted. These are not quite the same as I used for the calibration exercise, but they're pretty much the same. Remember I said they spread from eastern DRC, whoopsie daisy, eastern DRC through to northern Cameroon. The total number of individuals is about 19,000, spread across 223 village communities. And if you look at the cumulative distribution of infection levels, this is a random sample of 5 villages. Now, what I really mean by that is it's a sample of 5 villages that my postdoc showed me, and she swore that it was a random sample. But we did analyze all the data, as I'll show you in the next slide. So if we were being dishonest, the truth would have come out shortly afterwards. But of course, what you like to see if you're doing statistical modeling is patterns that are generalizable, that are reproducible. And so we are comforted by the fact that these distributions all have this characteristic convex shape. We're even more comforted by the fact that if you look at the red, that's an area with low prevalence, because 93-4% of the people tested were negative, and also the upper tail is pretty short. Whereas if you look at the green and the horrible colour, you've got higher prevalence and longer upper tails. So what that suggests is some kind of random effects model. I don't quite know why that keeps happening, but never mind, it's probably a good idea. Some kind of random effects model in which you've got 2 random effects here, one of which is driving the community level prevalence, and one of which is driving the probability that an inhabitant in that village will have at least T parasites per milliliter. And the point is that it's kind of obvious. None of this is terribly difficult by comparison with what some of my younger colleagues get up to, is that, you know, if you've got prevalence data, you can clearly in principle predict P, and if P and T are correlated, ergo you can predict T, and ergo you can calculate an honest predictive probability of the proportion of the individuals in that community who have infection levels of at least T, which in my case is 8,000. Oh, don't want to do that. Very low tech. Okay, so how do we build a statistical model? We do some exploratory analysis, and initially we simply look at fitting a simple, oopsie daisy, a simple distributional model with a positive probability at 0 and then a continuous probability. We fit a variable with a shape parameter less than 1 to get that convex shape. That's clearly not a unique choice, but it seems okay. And in fitting that just to separate villages, you can see the variability between villages there, in which the log odds of estimated prevalence varies over 4 logs, the log of the estimated scale parameter over 6 logs, but the shape parameter shows that Daniela, my postdoc, was indeed honest, because for 138 or 9 out of 156, the fitted shape parameter was less than 1. So taking a bit of a punt, we said, let's fix it as a constant for all the villages, but let's model the lambda and the rho as a bivariate random effect. So that's what we did. And when you do that, again, the natural scale for rho is the log odds. The natural scale for lambda is a log. U and V is a bivariate normal random effect. And if we do have useful covariates, the obvious place to put them is in the linear predictor in each case. Now, in fact, for the data that we were doing this on, we didn't find that the covariates we had available were terribly useful in a predictive sense. And rather pragmatically, because the people who wanted us to do this work were really hammering home the need for simplicity at every stage if we were going to turn this into something that could be operated in the field in real time, right? Coming to that later. We really didn't want too much complication. I'm not quite sure I bought those arguments completely, but anyway, we tried looking at a few covariates which didn't seem to be terribly helpful. I have my own theories for why that's true, and I'll say something about that later if anyone presses me. But the key thing is that these U's and V's need to be strongly correlated in order for this model to work, so that knowing the empirical prevalence allows you to effectively make inference about V. Okay, now that's a simple slide which could be made more rigorous by reading the literature carefully, as Vern Farewell pointed out to me a couple of weeks ago, a name that will be known to many of you. This is simply maximizing the likelihood fitting Weibels or gammas and looking at the difference and finding that the Weibel usually beats the gamma, so that's what we used. Okay, so now you've got a likelihood, and it's computationally, by modern standards, a very simple problem because we're postulating independent random effects in different villages. So the worst thing we have to do is a bivariate numerical integral. Gaussian quadrature works a treat, and so you can fit the model. If you do that, you get some parameter estimates. Remember I said the covariates in the end weren't too useful, and this is the one that we're relying on. The positive correlation between the two random effects. And that's what they look like graphically. And now we simply run through Bayes' theorem and we do our predictive calculation. So that slide is simply saying we have got a target for prediction, which is the probability that a randomly selected individual has more than 8,000 parasites per mil of blood. Handle turns, answers come out, and how does it work? So on this slide, for the same 5 villages, I'm showing you the predictive distribution of that probability. So this is a predictive distribution on a probability, and the black line is the 95% predictive interval, and the red line for comparison, because as I'll acknowledge very shortly, if I haven't already, there's a cost to making modelling assumptions. The red lines are what you would have got as confidence intervals for the probability that somebody has a parasite count greater than 8,000 mil per milliliter, had you have measured the parasite count on every individual. So my black lines are the intervals that only use the prevalence and the modelling assumptions. The red lines are the intervals that you would get if you weren't prepared to make those modelling assumptions. And the black lines are compatible with the red, but generally narrower. And therein lies both the advantage and the risk of making modelling assumptions. And some of these villages are small, so you have to be a little bit more careful with small villages. And I don't want to go through this slide in detail. It's simply saying that if you subtly change the question from what's the proportion of infected people to what's the actual number in this village, then you simply have to recognize the finite size of the village. And whether you need to or not, we just implemented a simple Monte Carlo calculation. Okay, so again, we thought we were done, and we wrote that up in PLOS NTD. And I went to the annual meeting of the people who are involved in this control program, and I presented the results, and the talk that came after me said, we've got a really nice, neat new device. Okay, I'm skipping this because I think I'm running a bit out of time, but I'll come back if I do have time. And wouldn't you believe it, you can do all this on a mobile phone. So what you can now get, thanks to some company in California and some clever people, is you can get a little microscope. You can see how big it is from this picture, and you can put a little drop of blood on the vision piece. You can slot your mobile phone in. You can press go, and it'll come back with an estimate of the number of mil per litre. Now, what's really nice, and forgive me if I seem carried away with my own enthusiasm, but really very, very nice, I think, to think about it, is that that mobile phone will have no trouble at all implementing our predictive algorithm. So the goal is to code up and put into the mobile phone an algorithm which, when you put a finger prick of blood, will give you the predictive distribution of the number of at-risk people. Will it work? Well, we don't know, to be honest, but they have started field testing, and I am going to go very briefly back to the slides I skipped, because this is what the field testing data look like. Now, you may, let's have a look at the good news first, remember that when I showed you 3 histograms before, now I won't go back, it's too much of a distraction, I think you can remember, there was a big spread in the log odds of prevalence, there was a big spread in the log of the scale parameter, nearly all the shape parameters were less than 1. So that's good. It looks like this new microscopy is behaving qualitatively like the old microscopy, which is what we'd want. Whether it's behaving quantitatively like it, we need to calibrate again. But the problem is, and here I have total respect for why, is that for practical reasons, they didn't go back to the same villages. They went to the red villages. And so we haven't got any direct calibration of villages, never mind individual people, whose blood has been analysed by the two technologies. But that's where you have to now come full circle and start thinking geostatistically. Because if you believe that these things are not just independent random effects, but are smoothly varying spatial processes, then you can make predictions from your traditional microscopy model, and you can calibrate those predictions against the actual results you get from the new microscopy, and you can decide whether how close the calibration is. Now, that's no excuse, if it's affordable and feasible, for not going back to the same villages, but the reality is that time moves on, people come and go, you're never going to get money to do a complete, gold standard calibration project, but if you can at least show that CellScope is actually capable of predicting traditional microscopy, by analogy with replacing blood samples by the questionnaire sampling, then we're in business. And so we've started doing some geostatistical analysis of these random effects. And so if instead of replacing U and V by U of X and V of X, in other words, let these random effects co-vary spatially, you can see that visually there is quite a lot of spatial correlation. That where you get highs, which are, the lows, it's more convincing actually. Where you get lows, which are the dark colours, you can see there's a certain sort of echoing across. It's far from perfect. You wouldn't expect it to be. If you remember, the point correlation was about 0.6 something. But that means that there is smooth spatial correlation. And I mean, that's important, I think, for two reasons. One is it allows us to have a bit more faith in our calibration exercise for the new technology. But more importantly, it means that actually it is wasteful to just make your decision on one village on the basis of what you measure in that village, because the neighbouring villages are giving you extra information. So you can make more precise predictions by exploiting the spatial correlation. So that takes me full circle, really. And all I want to say in conclusion is, as I said I think earlier, there's nothing special about geostatistics. But what I like about embedding geostatistics in what I rather arrogantly call principal statistical methods is that, yes, I'm making assumptions, but at least they're explicit. Whereas if you approach problems like this using ad hoc statistical methods, the assumptions are often kind of hidden. And personally, I kind of feel nervous about not having my assumptions up front. I'd rather have them up front and criticised than hidden in some complicated algorithm, the guts of which I don't understand. And we do have, thanks to the giants of the second half of the 20th century, including David Sprott, have plenty of theory that tells us once you've agreed that the model is reasonable, you can't do better than use principled methods of inference. And critically, when you make predictions, they're probabilistic predictions, they're not point predictions. And of course, there is no such thing as a free lunch, and I alluded to that before, but my favourite quote to summarise it is actually from a psychologist who says in one of his books, we buy information with assumptions. Now, I bought this suit recently. What do you think? It's all right? Not every suit I buy turns out to be a good buy. So you've got to be careful. But more importantly, and this is what keeps me vigorous and going to work each day, is you think you've finished and you haven't, because the world's forever moving on and we're always trying to just do a little bit better. In fact, that's my metaphor for everything I do, is I'm not trying to do the best, I'm just trying to do a little bit better each time. And with that, I will leave you with your thanks for your attention.
Does incidence play a role in this one? Or indeed, I guess in the early ones, if you look at prevalence and look at levels of infection for prevalent cases, just in terms of controlling and managing?
The generally accepted starting point for this study is that we are dealing with long-term prevalence in an endemic condition, and clearly in reality it must ebb and flow to some extent. But remember, it's vector-borne and it's in rural countries with no interventions, and the general wisdom is that you're almost by accident, because you can't of course take all these measurements at the same time, you are almost by accident doing a kind of time averaged version of a spatio-temporal process. And that's what they need, because we're talking about the program as a whole has been running for nearly 20 years, and it's got years to go before it'll do the job. So you've got to take a kind of temporally averaged view of the problem.
Yeah, so in terms of the side effects
Yeah.
issue, like prevalence relevant, if you want, in terms of controlling lower, say, then I guess incidence would have to be considered as part of a prevention program?
Yes, but in a sense that's a more ambitious goal than the program is engaged in. What it really wants to do is to have a better focus on where it needs to focus its scarce resources so that it can make operational decisions as to when it's safe to treat a particular area, and if it's not safe, and this actually is a decision that's usually made at an annual meeting in which there are both scientists and politicians, well, civil servants in the room, and there's a lot of country politics going on. So a particular country, there are 19 countries involved in this program, and a particular country may say, look, we really want, we need it now, and there has to be some kind of debate going on and discussion. So it's not precise science by a long way, but it's trying to inform those debates with honest assessments of what we do and don't know, and where we need to focus our scarce resources to turn predictive probabilities of a half into either 0 or 1. You know, the perfect map doesn't have any pink in it. It's all 0 or 1.
Can this model be used to measure the success of the program?
Yes, and indeed, given that I argued quite passionately that you can't expect carefully designed data sets in this operation, for all sorts of reasons, you know, field teams are continuing to visit these areas all the time, and they can and will continue to collect data. And, you know, slightly reversing my answer to Jerry, after a country has been treated, one would then be able to measure the change over time, and that can, should, and I'm sure will be done.
What would be the time frame to be able to?
Well, you'd have to do it on a time frame of years, because, as I said in answer to Jerry, this is trying to get a kind of an endemic prevalence estimate rather than a here and now estimate, and so you do need to recognise that there's an implicit time averaging in what you do. So you've got to essentially preserve that. The treatment regime is currently 1 pill a year, and some people think it should be 2 pills a year, but I think 1 pill a year is more feasible. And if you go back a year later after the distribution, you can estimate prevalence again. Yeah. Yeah, I mean, the methods, as you can see, are really just generalized linear models with spatially structured random effects, so they're generically applicable. So yeah, is the short answer. Yeah.
Any more questions? Please join me. Thank you again.
Thank you. Thank you very much.